without further ado, we'll bring you Dr. Walter Boynton from University of Maryland, and he's going to be giving this presentation on the impact of phosphorus on estuarine water quality. All right, would you like the lights down, son?
Yeah, a little bit. Yeah, that'd be great. Well, thanks for coming. I feel like a little bit of a fish out of water at this conference, but so be it. What I'm going to talk about is the impact of phosphorus, and then in small letters, nitrogen, on estuarine water quality. And the reason I put the nitrogen back in there is that so many times these two elements move somewhat in parallel with regards to their effects in these systems. So the long and short of it is it's a little bit misleading and it's incomplete to talk just about one as opposed to both. A couple of, you can read these things. I'll make a few comments on them. One of the issues with Chesapeake Bay that both makes it so extraordinarily productive is that it is pretty shallow. Tom Horton, who is an environmental writer, one time wrote that when you think about the Chesapeake Bay, you need to think thin. There's this ratio down there, 14 to 1. What that means is that there's about 14 acres of land that drain into every acre of Chesapeake Bay. And I can tell you there are many, many estuaries around the world that have ratios that are a little bit smaller and a little bit bigger than this. But if we change the estuarine area to volume, in other words, how much land drains into how much water, how big the bucket of water is that this stuff is draining into, Chesapeake Bay holds a global record. We have not yet found an estuarine system on the planet where so much land drains into so little water. There was a newspaper writer named H.L. Mencken, worked for the Baltimore Sun many years ago, and with regards to the productivity of the bay, he called the Chesapeake Bay a great protein factory from which we ate divinely. And I thought that was a pretty cool way of summarizing the fact that this is one of the superstar estuaries on the planet. Second thing is that if I had a magic wand, which I don't, but if I did, and I could tap that slide and turn all of the water in the Chesapeake Bay and its tributaries red, okay, so boink, they're all red, and then ask the question, how long would it take to flush all those red water molecules out of there? The answer would be that it would take 4 to 6 months. So what we put in the bay hangs around in the bay for quite a long time. It has what we would call a very, very slow flushing rate. Part of that is a result of the fact that we have small tides here. Our friends in South Carolina and Georgia and Massachusetts have tides that are on the order of 8 to 12 feet. And as we go farther up into Maine, they get up to 30 feet. So their estuaries effectively, through the tide, have an incredible flushing capability. So some of the things our Yankee friends have dumped into their estuaries over the years quickly wind up in the coastal ocean. Partly because those estuaries are short, and partly because they have this huge flushing. So you can almost think toilet. They really flush. Chesapeake Bay is about 160 miles long. It is a long way from Baltimore to the open and quote-unquote clearer, less enriched waters of the North Atlantic Ocean. So what we put in it tends to stay in it for, relatively speaking, long periods of time, even just in terms of the water that goes into it. And the last point is that many rivers connect the land to the bay. It is impressive. One time, occasionally I get, I'm a science guy, so I crunch numbers and I write stuff, and I get writer's block. And some of my best friends at the lab where I work are the boat crews. So I went down to the boat cruise one day and we started counting tributaries. And, we had nothing better to do. So we got to 60 tributaries, no problem with that. That's easy, And then I said, well, I wonder how many tributaries of tributaries there are. So we got to 600, we gave it up and went and have beer. The point is, even in Maryland, just Maryland, relatively small state, a small part of the basin, there's 8,000 miles of streams and rivers, 8,000 miles. So none of us live very far from the bay. So spatially, we're pretty connected, all right? 8,000 miles of rivers just in Maryland, but we're also connected really fast in time as well. The example I'll use is that the Susquehanna River enters at the top of the bay there. The headwaters of the Susquehanna in Cooperstown, New York, you know, Baseball Hall of Fame. During the high flow period, and for the Susquehanna River, that's January, February, March, and April in general, in the long term, that's when that river really gets up and flows, which the hydrology guy who just talked told us a lot about. And so if we were to throw a nitrate molecule into the Susquehanna River in Cooperstown during March, during the high flow period, it'd be in Chesapeake Bay 4 days later. So even though that place is a long way, it's over 300 miles from the bay, it gets there pretty quick. That's true for most of the tributaries during the winter fall, when most of the nitrogen, phosphorus, and sediment comes off the land and into the bay. All right, so wintertime, high flow seasons are very important. So let's talk a little bit about nitrogen and phosphorus, but particularly phosphorus. I'm going to show you a couple simple cartoons, and then we'll get a little closer to reality. All right, this is just a simple cartoon showing you what we believe, we're quite sure, Chesapeake Bay looked like in the 1940s, 50s, and part of the 1960s. And in particular, the plankton community. These are the algae and small plants that live up in the water column. Their populations were modest. The water was relatively clear. We use this device we call a Secchi disc. It's a plate about this big around. It's weighted and it's painted black and white. During the 30s, 40s, and 50s, there were many places in the bay where you could lower that down 20, 25 feet and still see it. That's unheard of today. Nothing even close. A second feature, so the water was clear, this plankton community was modest. There was a diversity of plants in the bay. All right? Right now, if we did a carbon budget for the bay, almost all of the carbon that's created in the bay comes from phytoplankton. It used to be that there were these rooted aquatic plants, about 700,000 acres of these plants, with about 13 different species. They range from freshwater up into the to the very salty part of the bay. They provided a lot of food material as well as habitat. And there were also plants that I can't show you because they were too small. They were called benthic diatoms. These are unicellular plants. They live in a little silica house, and they grow on the surface of the sediments. And one of the things that is very cool about these little plants is that they naturally make a lot of things that are called essential fatty acids. Us animals don't make that. To get it and grow, we need them. And they come from these benthic diatoms. So they were abundant. They were abundant because light got to the bottom over lots of the area of the bay. The bay in that previous slide I said is stratified. It's seasonally stratified. And what that means is that water, fresh water from the land, comes out of the rivers out into the bay. It's fresh. All right? Water from the ocean, salty water, is pumped by the tides into the bay. The salty water is heavier than the fresh water, so the fresh water more or less sits on top of that salty water that's coming into the bay. So we have two layers, so to speak. And because of this stratification, material that are dissolved in the water, like oxygen, for instance, does not penetrate very well through this stratification layer. That's something else to keep in mind here. What do we got now? This is not true for everywhere in the bay, but it's true for many places. The main stem, the Potomac, the Patuxent, the Choptank. And this is what we call a nutrient-enriched, overly nutrient-rich system. So what we have is a vastly increased plankton system, algae, in other words. We have a water column that's nowhere near as clear. The seagrasses have largely gone away. And these algae have short lifetimes, anywhere from a day to maybe 4 or 5 days in their toast. They die, they sink to the bottom, and bacteria start to decompose them. All right, so this is a lot like a compost heap. All right, it's an underwater compost heap. And one of the features of this decomposition is that if there's enough organic matter going down into the deeper water, and if that stratification is strong enough, which it almost always is, the bacteria will use all of the oxygen in the deeper water. And that's what we call a dead zone. So with this enriched bay that we largely have now, we have a loss of shallow water habitat. In other words, the seagrasses and those little benthic diatoms are gone. They're not totally gone, by the way. They're hugely reduced. And we've lost deep water habitat. You might wonder why the deep water habitat is important. Well, during the summertime, the surface waters of Chesapeake Bay get to be 27, 28 degrees C. That's right hot. Most of these animals here are cold-blooded, and so they respire proportional to temperature. And so many of them in the past might come up here and feed, but they're going to rest down here in this deep water. And that slows their metabolism down. They actually grow better. Okay, they're not just breathing it off. But this habitat is lost because these guys like oxygen as much as we do. So, here's another simple conceptual model. I think with this crowd, you guys will understand this graph probably better than I do, and that is fertilization tends to increase production. All right? And that's true in estuaries as well. If we start adding a bit of nitrogen and phosphorus, which nitrogen and phosphorus has always got into these estuaries, that's why they were productive in John Smith's time, production goes up. So it's essential for plant growth. I one time told an audience when I was showing this slide, I said, it aggravates me that so often in the press you see nitrogen and phosphorus being referred to as a pollutant. And what I told them is, well, you know, maybe not. I mean, it's nitrogen and phosphorus is the stuff of life. I mean, without it, we'd be toast. And then I thought, no, actually we wouldn't even be toast, because there is some nitrogen and phosphorus, not much, but there is some in toast. So, you know, I'm not trying to downplay the problems with nutrient enrichment, but you know, they are essential, absolutely essential elements. So they're essential for plant and animal growth, and within limits. Increased fertilization increases production. So this is what we get here. This is where some parts of the bay are now. We call it eutrophic. It's overly enriched with nitrogen and phosphorus, and we get a bunch of negative things happening. We get algal blooms. Some places, odors of hydrogen sulfide. Rotten eggs actually emanate out of the water. There's a loss of oxygen in the water. That's the dead zone business. And that's important. That's one of the key things, is low oxygen is an ecosystem killer. We got decreased water clarity, and if there's a second ecosystem disturbance in an estuary that's really important, it's this increased turbidity. We've lost seagrasses, and there are ramifications for food webs and the way material moves to the higher trophic levels. So, one of the key management questions in the bay is, what is the optimal level? And as many of you know, there is this large TMDL that's underway, and when you sort of cut everything away, what that's trying to do is to decrease the loading rates to the bay by about a factor of 2. About cut them in half from the baseline in the mid-1980s, when it was about as high as it ever got. All right, so all of this is nice and simple. These are cartoons. The question is, how does it really work? So what I'm going to do is I'm going to walk you through the way that we think this actually works. And what's important here is that these ecosystems, probably like corn and soybean fields, are not just a simple set of linear cause and effect. There are feedbacks that can really change the story. So here we go. This is degradation. This is the way you get an estuary into a nutrient obese situation. So you add more nutrients, both nitrogen and phosphorus. That grows algae. The algae and some of the dirt that comes with this create turbidity. So the water is no longer very clear. The algae sink, decompose in the deep water. So we have cracks. Okay. So we have less oxygen in the deep water. Now this mumbo jumbo here, lower redox nitrification denitrification, what I'm basically saying there is that when there's no oxygen in these deeper waters of the estuary, the chemistry of the water and sediments change. All right, and I'll show you how they change in a minute. So what happens is these processes, which tend to sequester and get rid of both nitrogen and phosphorus, stop working. So we get more recycling of nitrogen and phosphorus back into the water. So without increasing the amount coming into the bay has now more NNP to work with. All right, so a eutrophic bay can become more eutrophic when these processes shut down. That's a negative feedback. It is causing something to go faster when we actually want it to slow down. So with more turbidity, there's less light, there's less seagrasses, there's less of these little funky little diatoms on the bottom making good stuff. So there's less nitrogen and phosphorus uptake because they're not there anymore, sequestering it. And these diatoms and seagrasses act a lot like fly paper on the bottom of an estuary. They tend to keep sediments on the bottom. Okay, they're sticky. And when they go away, those sediments become more prone to wave, wind, erosion, which, you're probably getting this coming out, has a positive feedback on water clarity. So the water is now getting cloudier, and we haven't changed the inputs. Okay, and finally, we have some disease and harvest issues. We've got a degraded oyster system, and because those oysters, and I might add here, it's not just oysters, it's all of the assemblage of benthic organisms that filter the water. So we're talking about clams and mussels and little tunicates and all kinds of creatures. They are no longer sucking the water, filtering it, so we have more turbidity. And we have sea level rise going on. And marshes are eroding. When they erode, they are no longer taking up and sequestering nitrogen, phosphorus, and dirt. And they're also adding material back to the water column, which can grow more algae. So this is what really seems to happen. It took a couple decades to get all of this into the water quality models that are currently being used. That's a slow process to work all this stuff out, but it seems like this is the general pattern of what happens when we put too much nitrogen and phosphorus into an estuary and start to degrade it. I wanted to show you something about, many people here know a lot about fertilization. I don't know anything about crop fertilization, but I know a lot about estuarine fertilization. So what I showed on this slide here is the total phosphorus load, the total nitrogen load to a whole bunch of estuaries from various places around the world. Those are the black dots. All right. I've also have this gray area here, which indicates typical nitrogen loading rates to a variety of terrestrial landscapes, not just cornfields. This is a variety of landscapes. That's why it varies by almost an order of magnitude. In any case, what we can see is that these coastal and estuarine systems, the amount of nitrogen and phosphorus coming to the land, getting into these systems, varies for nitrogen by 2 orders of magnitude, for phosphorus 3 orders of magnitude. And if we go and look at one system, this is the Patuxent River, in between years, those loading rates vary by at least a factor of 2. So this is a really variable, dynamic environment. That is one of the reasons why monitoring for us is so important, because we have got signals that change a lot from one year to the next. Okay? This little green square up there is the Back River Estuary. It's a small tributary of the bay just north of Baltimore. The basin is 40% cement, and it has a sewage treatment plant that is actually quite famous. It started operating 103 years ago. One of the first sewage treatment plants, not the first, but one of the first ones in the US. And it started working because some people in Connecticut got sick over eating some tainted seafood. Also because the city of Baltimore had a giant fire, and while they were rebuilding, they said, oh, what the hell, let's put in the sewage lines. So they did. And this place has been discharging various levels of treated wastewater ever since. There has been recently, in the last couple of decades, some absolutely wonderful engineering that's gone on there to decrease these loads, even though the amount being discharged is going up. In any case, the interesting thing to try to get you guys thinking a little bit is that I took the Back River units, the kind of units we use, and converted them into something I think that you're more familiar with, which would be pounds per acre per year. And in the Back River, we're talking about a nitrogen load of about 900 pounds per acre per year. That's, from what I've been told, a pretty substantial fertilization rate. And you can see there are places in Western Europe, the Shell, Boston Harbor, before they fixed their storage problem, are even higher. In the case of Boston Harbor, what they did was they used the engineering fix, and that is they gathered all that storage up, put it in a pipe, and shipped it out to the North Atlantic Ocean. So in that case, the engineering principle was that dilution was the solution to pollution. In the Chesapeake Bay, with this horrendously long water residence time, it's really not a very good option for us. So, just to give you a sense of the amount of NNP getting into these different estuaries varies a lot. But while there's always, I suppose this is true with ag extension agents. I mean, you guys probably have some disagreements, about what's what. Well, we certainly have those in the science community. At times we really spin our wheels. But there's one thing that we're collectively sure of, and that is that if we add more nutrients to these systems, we can wind up like this. We've already wound up like this. This is the Potomac River estuary just downstream of Washington, with an intense, what's called microcystis. It's a toxic algal bloom. And the guy I was with just put his hand on the surface of the water, took it up, and we took a picture. We don't want that, but we could get there more generally if these loads go up. And our Chinese friends have done lots of experiments with dumping a lot of nitrogen and phosphorus in their coastal water, and that's a beach. I would not want to go there. In fact, I haven't been there. A friend gave me this picture. But you can see people sort of breaking up the algal mess to get in the water. We are pretty much in collective agreement that, if we wanted to continue to enrich these ecosystems, this is what we could get, or something akin to it. All right. I babbled on here a little bit about nitrogen and phosphorus, and one of the key reasons I babble on about both of these instead of just one is that they are both incredibly important in driving the production of this system. Ag audience, no surprise to you guys, it's true in estuaries as well. So early on, the science of this nutrient business was that actually in the 1950s, the dogma was you cannot pollute estuaries, therefore let's not monitor or study them. The reason you can't pollute them is they're connected to the ocean. They flush, okay? It was hard getting any funding back in those days. And then engineers in particular took the lessons learned in some lakes that said phosphorus is the key element, controlling productivity. So you only have to worry about phosphorus. After lots of work was done, we finally came to the realization that in most of these coastal estuarine systems, both are important. They're important at different times and in different places. So, what this little diagram here is showing you is that up here at around 200, that's where the Susquehanna River comes into the bay. So, way upstream. 0 is the ocean, Cape Henry, right? And here, we have the time of the year. So if we go up to the upper bay in the springtime, phosphorus is rolling and controlling the degree of algal growth. Right? It's real important in the late winter and spring. So when light is not limiting, phosphorus is. And in fact, for most of the bay, for a brief period of time, phosphorus is the ruler. We add more phosphorus at that time of the year, we'll get more algae, right? Which is not what we're looking for. During the summertime, and even in the upper bay, nitrogen is running the show. And as we move down the bay, the period of the year where nitrogen is crucial increases. So, fortunately, in this estuary, we have what we call a dual nutrient reduction strategy. That is, both of them need to come down to move us back to an ecosystem that has diversified primary producers, limited or very little dead zone, light getting to the bottom over much, much bigger areas. That's what we're aiming at. So, this is one of the reasons why. Okay, I mentioned earlier that one of the things that's really, really key is getting oxygen, both down into the deeper water and to the sediments, all right? So I'm going to show you this funky little diagram here. I'm going to show you two of them. And let me explain it. You all know what this is. That's dissolved phosphorus, the kind of phosphorus plants can use. POP really is algae. So when you see POP, think algae. All right, so this is under normal, good oxygen conditions. And so let's go see what happens to phosphorus when we start out in the growing algae. So algae take up dissolved phosphorus. They're up in the lighted part of the water column where they can grow. Those algae have a short lifetime. They fall to the bottom. So now we've got algae on the bottom. The bacteria decompose those puppies. So we get phosphate, okay, now in the pore water. Okay, but we also have oxygen. We've got oxygen in the upper water, the lower water, and in the sediments. And there are a lot of animals in the sediments that are squirming around all over the place, making burrows, which really injects oxygen even farther down into the sediments. So, you know, this far, and even sometimes this far into the sediment, those sediments are just as brown as can be because of the animals. All right, so what we have then, we've got iron-rich sediments in the Chesapeake and lots of East Coast estuaries. That oxygen that's down there reacts with the iron to form these what's called iron hydroxides. And those iron hydroxides, what they do is they grab that phosphorus that's in solution, bam, get it, and it adheres to the soil particles, basically. It's not dissolved anymore. And because it's not dissolved anymore, it is not going very far. So we measure very small phosphorus releases from these sediments, okay? So that's, and what happens to this phosphorus that's bound to the iron particles is that it gets buried, all right? In a way, it's on its way to making coal, well, not coal. You know, it's out of sight, it's out of mind, it's gone. It is not in the biological system anymore. All right, so let's go to the bay that we got now, all right? So here we have phosphate being taken up by the algae deposited, some oxygen getting through the decline, but no oxygen getting into the deep water, no oxygen in the sediments, no ferric hydroxides. What does happen is that a whole lot more phosphorus starts to be released because it's not binding to these iron particles, all right? And in fact, it gets worse. When the oxygen goes away, in all the salty parts of the bay, there's a giant tribe of bacteria that use sulfate in place of oxygen, right? Not very attractive to us, very attractive to them. And what they do is they metabolize organic matter. The end product is hydrogen sulfide, right? Rotten egg smell, right? So when you smell that, you know you got a really pretty enriched system. And the reduced sulfur compounds just kick phosphorus right back into solution. The iron particles make pyrite, fool's gold. And that is chemically a much more attractive compound than the iron hydroxides with phosphorus attached. So phosphorus gets kicked back into solution, and we got this enormous positive feedback going. That is one of the things that we got to stop. The way to stop it is to decrease the loads, which will help get more oxygen into that bottom water. And we actually, that chemically is pretty well worked out, by the way, but I always like to see, well, it would be like a field test for you guys. So people went out and took lots of measurements in the bay, and when oxygen in the deep water was high, like it is in April, there was very little phosphorus in the water column. May, the oxygen starts down, more phosphorus. June, oxygen's pretty low. Boom, July, it's out of sight, and August, it's even higher. So what we need to do is to slow that cycle down. That's part of that degradation trajectory I showed you. So, what does the restoration look like? Okay, I'm not going to bore you guys too much longer. Okay, so this is the way this works, all right? And these sort of pathways have been incorporated into the water quality models. So a lot of blood, sweat, and tears that go into getting this stuff into those models. So we've got less N and P coming into the system, which develops less algae and turbidity. We have, or others, people, the community have done lots of work with trying to relate nutrient loads to algae and estuaries. And guess what? It's true. It works. Sometimes it has to be scaled a bit, but that's the message. Add it, you get it. So take it away, we're convinced that we get less. So more light is getting to the bottom, more benthic production, more nitrogen and phosphorus is taken up because these plants are there, they weren't before. There's less resuspension because they're sticky like we talked about. And we've got a water clarity feedback started. There's less recycling of NP. And that's a nutrient feedback. So when nutrients come in, they don't just go blasting back. There's more water, oxygen in the deep water. There is more nitrification and denitrification. That is the bacterial process that basically takes ammonium, moves it to nitrate, that's nitrification, and the nitrate can be denitrified, back to N2 gas, that goes back to the atmosphere. There's a lot more of that happening. There's an accumulation of those measurements in the bay now. And what we're really pretty certain of is that those rates are close to zero. They may not be zero, but they're so small we can't measure them when there's not oxygen in the deep water. When there's oxygen in the deep water, these rates can go right off the chart. So with this, there's less recycling going on. We are in a restoration mode in the bay. The Harris Creek Oyster Rehab Project is apparently the biggest oyster rehab project in the world. It's a great experiment. We're going to see what happens, and hopefully it will spread. So with those guys filtering, there's less algae, there's less turbidity, and if we start expanding tidal marshes, some of this shoreline restoration that people are thinking about, the idea there is that they will take up nitrogen and phosphorus, suppress resuspension, and get us even clearer water. So that's what we expect to happen as we start marching down this restoration pathway. We have seen some of this, and what I'm going to do to finish this talk is to give you two examples so that you have some sense that what I'm talking about is not just theory. So the first one comes from Matawan Creek. It's a small tributary of the Potomac River, about 20-25 miles downstream of Washington, D.C. One of the points I like to make with this picture is that there's lots of both emergent and submerged plants in this picture. Enough measurements have been made now to really be pretty convincing that these kind of places, these wetlands, whether they're tidal or not, act much like a kidney. That is, they remove stuff. The rate of removal of nitrogen, phosphorus, sediment, in many instances is just spectacular. So anyway, this is Matawan Creek. This green line here indicates algal abundance. So it goes back to 1985. There are a few measurements prior to 1985 that are a little bit off the chart. They're up around 50 and 60 units of algae. 2 points. One was that there was a major wastewater treatment load reduction that took place in 1996. And there was a serious drought year. I think it was 1992. So what we're seeing here in that 1992 thing is a sudden decrease in the amount of material coming off the land because stuff doesn't move off the land when it doesn't rain, or at least it's suppressed. And then after the wastewater reduction, what we see is a decline in chlorophyll to levels that are really what we want to see, maybe 4 or 5 of these units. So that was pretty good. When those algae went downhill, water clarity went up. So the water started to clarify, and seagrasses, the big green bars, just exploded. They cover about 40% of the creek. And Matawan Creek is known as one of the top 10 largemouth bass fisheries in the United States. Not a bad restoration outcome. In fact, that's a really good. So we see these systems responding. Sometimes there is a lag between when we do something and when the system responds. Sometimes the lag is pretty brief. My sense is that the lag for phosphorus reductions will be longer than the lag for nitrogen reductions. And one of the reasons for that is that nitrogen's got another pathway to get lost, denitrification, and we can't dephosphoritize phosphorus. So it needs to get buried. That's a bit of a slower process. So an example from a tributary. Let's go to a big example. This is a place called Susquehanna Flats. It's a large area of the upper bay where the Susquehanna River enters the bay. It's 3 to maybe 6 feet deep. It covers an area of about 25,000 acres. And it provided us with another example of why monitoring is important. It is one of the ways we start to see change in the bay that are pretty unequivocal. And also it's an example that reminds us that once these habitats start to get better, strong positive feedbacks can accelerate the restoration project. So in other words, one of the concepts, and I think it's a real good one, is that if we can get the loads down enough so that good things start to happen, then the good things that are happening will reinforce the good things and we don't have to do a lot more. Okay? That's positive feedback. So let's take a look at this Susquehanna Flats business. Has anyone here seen the Crocodile Dundee movie? Yeah? You remember the scene where they're walking down the street in New York and this hood comes up and pulls out this little stiletto, and the Australian guy just looks at it and he reaches behind himself and pulls out this machete-like thing and it says, now that's a knife. All right, well, that is a seagrass bed, okay? This is not your wimpy bed. This bed covers around 25,000 acres. You can see it stretching almost off to the horizon there. The water is clear, you can see that here. This is what we think it looked like in the 1950s. It's there now. So, how the heck did that happen? Well, monitoring data. Aerial surveys are done of this and all of the areas of the bay on an annual basis. This light yellow color, what that indicates is that if you looked hard enough, you could find some sprigs of seagrass. Hardly a seagrass bed, but you could find them. It was really, really very sparse. And that pattern continued up through the 90s, kept going, and we start to see some change in 1999. And what happened? Well, in the Susquehanna River Basin, in the fall of '98, the rains did not come very much. So we went through a period of a number of years of very suppressed river flow, particularly during the winter and spring, okay? We were in a drought situation. So this bed was experiencing far better water quality than it normally had seen. That's point one. Point two is that the concentrations of nitrogen and phosphorus in the Susquehanna River have also started to come down. They started coming down in 1989. And they haven't come down enough yet, but they are coming down. So what was in the water was less potent. So less water, less potency. And we start to see an expansion of this bed in terms of density. And by about 2007, 2008, this was a massive bed. In fact, it was so massive that the water downstream, okay, had improved water quality. In other words, it was acting like a kidney. It was taking up lots of nitrogen and phosphorus, sequestering dirt. I should also tell you that many of you probably remember 2011, two hurricanes, or a hurricane and a tropical storm came through, and the second one, the tropical storm, Lee, produced, it's either the second or the third highest flow ever measured since 1929 at Conowingo. I think it was the second biggest. Agnes in 1972 was the big mother flow of all times, and that got to be about 1.2 million cubic feet per second, and Lee got to around 800,000, so nothing to, it was huge. And what that huge flow of water did was it cut a whole bunch of channels in this bed, okay? Just like somebody drove a bulldozer through it. So I think many of the people working on this thought, oh, that's the end of that bed. They were wrong, okay? 2 years later, the bed looked much like it did in 2010. So in this case, the bed had a long enough time to start to build root systems. So there was this built-in resiliency that they really weren't that clear about. So when conditions got better and the bed started making conditions better again, those roots kicked in and boom. About 3 years after Lee, it was hard to tell that that kind of disruption had occurred. So that's another thing we're looking for in restoration, is some kind of resiliency from things that we know are going to happen. I mean, it's going to rain hard, there are going to be big flows. So what do these systems do? Well, we think that a real healthy estuarine system's got a certain amount of resilience, and you know, it takes a punch and it gets back up and carries on. So let's finish this off. I think from the estuarine coastal marine science community, we think the basic ideas of enrichment and restoration are reasonably solid. That means we can act on it. The dual nutrient strategy is sound. Both N and P play powerful roles in the bay water quality. Substantial reductions will result in improved water quality and better habitat conditions. There are small examples and there are big examples that have happened in Chesapeake Bay and around the world. Okay, so the confidence level in this scheme has gone way up in recent years. The pathways estuaries follow during degradation and restoration often involve time delays, which means you do something and nothing happens for a while. Abrupt changes, we call them thresholds, where when you add one more molecule of the good stuff, boom, over the cliff you go. Those are thresholds. And other things that are not fully known or understood. So what I mean by that is we're going to have some surprises along the way. We haven't done this before, so there'll be some surprises. And restoration trends, well, I've already said, have been observed in both small and large Chesapeake systems and around the world, and those are really, really good signs. I'm done. Thanks for your time.
So does anyone have any questions? Any questions?
Your 25,000 acres of the Susquehanna Flats there, is that area growing as well or not?
Yeah, good point. The answer is it is now growing very slowly. Why is that? The why is, if you look at the topography of Susquehanna Flats, it is flat and shallow, and then it starts deepening. So this stuff is now growing down into deeper water, less light, more erosive current velocity. So it is, to some extent, it's still moving outward, but slowly. So I think it probably won't grow much bigger, and I'm not sure it can get much denser because it is. The folks have put on, snorkels and swimming around down there. They say it's like Humphrey Bogart and the African Queen, incredible.
Are those the traditional SAVs from back in the 50s and 60s too?
Good question. Yes, but there's also some invasives and exotics mixed in. So Myriophyllum is in there, Hydrilla is in there, but so are a half a dozen obligate freshwater species. The first invasion that we saw of Myriophyllum, Eurasian water milfoil, was in the 1960s. And during that time, the bed was like it is in 2010, like I showed you. That bed went like this, the exotic went like this, and by the end of the 1960s, everything was gone. Well, down to very, very sparse. I think we'll see a lot of the seagrass resurgence in places like Susquehanna Flats, Upper Patuxent, Upper Potomac, Upper Choptank, whenever we get a little bit of nutrient reduction, because up in these smaller streams, there are very big seed banks, and so they get reseeded really quickly. So they're probably reseeded every year, and when conditions are right, they come. Yeah.
What do you think the time scale is for those other bigger areas coming back?
Yeah, I don't, let me put it this way. If I had a magic wand, right, and I could cut the load from the Susquehanna River in half now, right, the response we would see that summer. In other words, really very quick. Now, so I think big response and then slower response, right? But we are sure that the response will be reasonably quick. And the reason we know that is that we've had these natural experiments for the last 30 years, wherein river flow varies between flood and drought conditions. So we look at the response of the bay under those conditions, and the response is interpretable, and it's very big, and it's very fast. We had the, we didn't know Agnes was coming, but we had this program of measuring algae out in the mid part of Chesapeake Bay for about 2 years before Agnes showed up in '72. And the summer of '72, so a month after Agnes, that algal crop started to get big. And then the next year, it even got bigger. I mean, it was monstrous. But that was it. The third year, so we had Agnes, 1 year post, 2 year post, it was back to normal. And that was after Agnes, which was a monster event right at the beginning of the growing season. So there's lots of evidence to say that this is, if the loads come down, okay, now this is not load reduction in model world, this is load reduction in the real world, then we should see responses pretty doggone quick.
You talked about that feedback mechanism on the phosphorus, and you have the high phosphorus load, and it's kicking itself back. So, I mean, phosphorus is gonna...
Not if there's oxygen at the sediment surface. There is some phosphorus that's always going to leak out of the sediments. But I won't bore you with the units, but we measure like 1 to 5 units when there's oxygen in the water. When there's no oxygen in the water in the sediments, we measure 50 to 150 units. Those are the kind of changes that take place. Big, real big.
Okay, one more question over here.
I was just wondering, what year was the last year where the bay was like good, like you said, 30s, 40s, 50s, and then when did it fall?
Good point. There was a jump in the dead zone in the mid-1980s. So, and then there was another jump at 1970. So prior to 1970, we almost the data we have indicated no measurements of really anoxic water. That is oxygen 0. Okay. Between 1970 and 84, anoxic water was recorded almost every year. And then after 84, there was another jump. And that looked like it was not due to a change or increase in nutrient loading, but rather a change in the prevailing summer wind directions. Yeah, it's part of these longer term weather patterns where for many years, for a number of decades, the summer wind was primarily out of the southeast. And what that meant was that the bay tended to mix a little more, enough to suppress some of that hypoxic water formation. Then it switched into the southwest, and the effectiveness of that wind on mixing processes is much less. So, does that answer?
Yeah.
And nowadays, in the last 5 or 6 years, there are these subtle indications that hypoxia, well, this is not subtle. Hypoxia is not lasting as long as it used to. It does not extend as far down the bay as it used to. Nitrate is showing up in the deep water when it was never there, and the only way you can get that in the deep water is to have nitrification, which requires some oxygen. We see a radical decrease in ammonium concentration in the deep water. That is super duper good news. So these things are not happening, big time because the loads haven't changed big time, but they've come down. And so we're seeing these subtle responses, which are pretty heartening.
Yeah.
Yeah.
Okay, thank you.
Sure.